Yeah, it worked.
Alright. How changing my topic to that? Alright, so here's how this is going to play out. So, the overall final, and I mean final, over everything.
Wait, midterm one?
Including physics.
Like, everything.
The final.
Like
end of the year.
Like
At
you
the
don't
end
know.
of the year.
Like,
End of the
end
year.
of the year. Wait.
Yes, end of the year.
Full gravity, centrifugal motion.
What?
No, that's not fair. No, you can't
Wait.
do that.
The washing machine.
Are you doing this?
No, stop.
Hey, listen. Hey.
There's a reason there's 2 AP exams.
Wait, he's gonna add
One
one.
second.
He's gonna start adding something.
A meter revolving around
I'll
kill you
I
now.
don't want centrifugal motion really real.
We just make that.
Mr. Burkham,
Washing
there's one exam and 82
They all add
exams.
on.
There's too much.
No, there's no point.
Wait. You didn't finish your thought though.
But it's gonna be big ideas. It isn't gonna be like.
We're gonna have force buoyancy.
So is buoyancy gonna be on here?
Oh, thank God.
I won't put buoyancy on.
Wait,
so it's not overall the big
Ian
ideas.
Bernoulli's stuff gonna be on there.
Oh my
There's
God.
Bernoulli stuff.
It's not gonna be on the
Mainly because my honors
Bears.
is
That's right. Let's go.
California prospect, he has a chart. He paints a
What
chart.
is the momentum?
And
No.
then he looks through a lens. It's a convex lens.
So
Wait, so when's this final?
most of it, the vast majority of it is going to be stuff from the second half.
Good.
Okay, optics, harmonic motion. Okay, electric field. So the last thing that we need to cover, and this is what we're going to start today, is chapter 21 on electrical potential energy. That we're not going to have a separate test over that. That's going to be just included in the course. Okay, so there will not be a separate test over chapter 21.
So just like extra.
Well, it's just going to be included in it.
So it's just a midterm.
Everything from the first day of AP Physics.
Yeah, pretty much, yeah. Except for
No lemming problem.
And that's on Friday? Everything from August.
Thursday?
Why is it not at the end of the year?
Bert, what if I didn't take AP Physics 1?
Boo-hoo.
it's not, Nathan, it's not going to be any, I will not ask you anything specific that
Oh, okay.
Physics 1 covers that you did.
Okay.
Okay? So that's what I said, it's not going to be Bernoulli's equation, it's not going to be Big Mike.
Is there a question where there's like you have the tire shift on the base?
Oh,
There's like it's like going horizontal and then it goes up a ramp. and it's going back horizontal.
What the hell are you talking
Like inclined planes?
Yeah.
Might be.
about? Oh!
There might be energy on it.
incline is
Will there be
easy.
so
What
like
is
one of the
it?
tires right goes like incline
What?
horizontal?
Bert,
That's
the second time you
easy.
input
Where's
a
normal?
grade
I've
that
never
you
done that
wrote.
one.
On Skyward it says 50, on this it says 57.
That's a
For both
bit
meetings.
of a
Lab.
You didn't.
I think you should
Okay.
take off.
Did you the grade user?
We should degrade them.
Is rotational stuff gonna be on there?
Yes.
Ryan, what did you think?
Wait, moments of inertia?
I did terrible on this stuff.
boy.
Oh, I don't like
You
that.
want to drop out.
Big
You want to
idea.
drop out too.
Okay, like if you're spinning, for example.
Okay. I have a question. So which, okay, depending, this is actually a good question. So depending on the ratio, there's questions that are like think about it, and actual response questions, what's the ratio?
On
Like there was one or two big response questions.
Okay, that's not bad. Okay, I'm asking.
That's really big ideas.
Alright!
Would there be acceleration problems?
Oh god. Oh god.
Wait, is this for this midterm?
Oh no!
Wait,
Guys, what is
Ryan,
F equals
is this for the
M?
midterm or the final?
Popcorn?
Would there be a review?
Yes.
Okay.
Ryan, what else?
Not like
We're talking about the final
Yeah,
stuff.
game review.
There's no package?
So,
Auto messages should have.
Here's what we've got. So we'll spend today, Monday, Tuesday on chapter 21. Okay? Review
Oh,
Wednesday.
the midterms this week.
You mean tomorrow this week?
Really?
Tomorrow this week.
Midterms on Thursday. We're gonna chill out on Friday.
Oh, it's right there.
I'm gonna be gone
Let's say
Friday.
Environmental.
Sorry, I'm
Video I want you to watch.
I'm replacing research today.
I mean, also like.
So there'll be no homework over spring break.
Let's
What,
go.
Big Mike?
Is there so going back to the whole final, is there a lab final?
No.
There's no lab final.
We have to recreate the glove foil experiment.
Yeah, there you go.
You gotta go.
Oh, yeah.
When you call this the final, do you mean midterm and we'll have more
Probably the
units,
final.
or is this the final unit? Like, we
What?
have more.
I have no idea.
Why are you calling this the final?
Right,
as
which color
opposed
are you
to a
talking
midterm?
Because it's gonna cover everything that we've covered.
Wait, so
We'll
Also,
still have
this is
more
a-
after.
Oh, yeah.
Okay.
No, we're not gonna learn anything more
I
than.
didn't know if you were
Let's
saying for like
go.
AP to.
No.
Okay.
Oh, so this is this one. That's fine. No.
I'm just confused.
So we're gonna
Oh,
have,
it's
we're
like the
gonna have
final,
another
final.
final?
Your
Wait,
dictionary
you all are making me.
Wait, this final.
I
that
think
midterm,
midterm-
that's just
And after this is that midterm final thing. We won't learn anything more.
It's anything from day one until Tuesday.
You mean Wednesday?
You mean day one?
Yes.
I mean Tuesday.
That's the final we're talking about. I thought we were talking about like the actual.
Yeah, that's
final,
right.
at the end of the semester.
No, we're not gonna have a final at the end of the semester.
Wait, we're not?
Because it's over 3 months, so it's already really hard. Yeah, we are.
Okay,
My lemon's
Let's
fine.
go.
so.
You throw a ball.
Velocity.
Okay,
What?
No, remember the like the air thing?
yes.
Oh.
What'd you say this unit was called?
Hush. What?
What'd you say this unit was titled?
What'd you say, what?
Electric
What?
potential.
Electrical
Just electric
potential
potential.
energy.
She's asking what the unit was called.
Chapter 21.
You want that one inside there?
Okay.
Sorry, Bird.
I'm telling you, Mr. Bird, we should take out that.
No, I just totally don't. Okay, so this unit on chapter 21, which is on electrical potential energy. So there's a couple of things that make this tough, okay? Especially if you compare it to like normal energy. So let's kind of have a refresher about energy. So if I take this baseball and I lift it up, all right? Let's start with this. Did I do work?
Yeah.
What?
Force over distance.
I exerted the force over a distance, right? So remember, broad idea of work is that you can express work as a couple of different ways. One is that it's a broad idea of a change in energy, okay? And that change in energy could be potential energy, like I lift it up. It could be kinetic energy, I throw it, I change the kinetic energy when I catch it. You could talk about energy stored in a spring, okay? Any number of ways that you can measure energy. If I make it spin, now it has rotational kinetic energy. So, translational kinetic energy, remember, is 1/2 mv squared. Rotational kinetic energy is 1/2 I omega squared, right? But no matter what, no matter what it is, what's any type of energy measured in? Joule. Okay? So this would be kilograms, meters squared over second squared. Speaking of moment of inertia, what are the units for any moment of inertia?
Kilograms meters squared per second. Kilograms meters squared.
Moment of inertia, what's the most generic way to express moment of inertia?
Kilogram squared meter. What happened?
mr squared.
Kilograms meters squared.
So any moment of inertia is going to be in kilograms meters squared. Now, added bonus. What's the only time you can use mr squared? There's two situations.
If it's
Oh, it's a point
Point mass,
Or if
Fin
it's a.
or a
Then
Yeah,
who?
Fin who?
yeah.
Give me mine.
Fin who? Point max. That's the only time you
You tell us
can
in
R
one
squared.
square.
Plus one.
And no, I'm not going to extend it.
Am I money?
Throw it out.
Bert, I don't know why you're looking at me like this.
Because I looked up and you were talking.
I said the right answer both times, and you act like I don't exist.
You're not a person.
So I'm making sure I wasn't muted.
Yo,
Trust me.
Sorry.
I heard you. Okay. So, any moment of inertia is going to be mass times some radius squared. This only works if it's a Van Hook or a point mass. Do not spend time memorizing the equations. I will give you any moment of inertia equation that you need. Okay? You just have to know how to use them. All right. Now, let's say that the ball has a mass of 0.5 kilograms. And I lift it up to a height of 2 meters. How much work did I do?
One.
One?
9.8.
No, hang on. Let me chill.
9.8 joules. 9.8. Use the calculator.
No, we don't need to.
Okay?
I need
So,
to-
could I just take 0.5 kilograms times 2 and get 1?
Yeah.
No, wait.
No.
No,
Because you need G in there.
because the units don't work out.
J.
Okay?
Hey, grams, meters, what is that?
Well, you can do that.
So, yeah, if I just multiply together, I'd get kilogram meters. So, work is also force times distance. So, force distance is Newton meters. Okay? Cool with that. So, since that has to be a force, if I take 0.5 times 9.8 meters per second squared, I'm going to get 4.9 newtons times 2 joules, or 4.9 newtons times 2 meters gives me 9.8 joules. So at this point, it has 9.8 joules of stored energy. I drop it. What's going to happen to the ball?
It'll accelerate.
It's going to accelerate. What's going to happen to that kinetic? What's going to happen to that potential energy? It's going to change into kinetic energy, right? So you can imagine a container of potential energy and a container of kinetic energy. And that's just going to transfer over, right? Okay. So as the height decreases, you decrease UG, you increase the kinetic energy. Easy peasy. Now the work that I do is equal to either that change in kinetic energy or it'd be the change in UG as I lift it up. They might big picture kind of thing. Is there a possibility of any of those being negative?
No.
No. Okay? Because everything's positive. Height is positive. Even if you have a negative velocity, that's squared, so that's going to be positive kinetic. Cool. Now, it's a little bit weird. So the idea for gravitational force is big G M1 M2 over E squared, right?
Yeah.
Cool. Now, why does that work out to be newtons?
Oh, G is like kilograms
Mass squared over
Because
distance
G
squared.
is
Well, big G has what?
It's like
Newtons?
meter squared over kilogram.
Meter squared over
Kilograms.
kilograms squared.
You're gonna put 9.8.
And then you have kilograms squared over
meter squared.
meter squared cancels out. Those cancel out. You're left with newton.
Oh yeah.
Now, what if we change it? The equation. We're going to make it big G. You have mine?
Yes.
Put that phone away before I turn it into a projectile.
Oh, I'm so sorry. It won't happen again.
Okay?
Yeah, there's only one D.
Now, let's just say I divide by D. Just chill out.
Wait, the meter's on.
New
Newton
meters.
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 You just did your meter.
Okay? Because that's going to be newtons meters squared over kilogram squared times kilogram squared, but then I'm going to just divide by meters. Yes. And then you just get newton meters, otherwise known as, which would be a measure of energy. Okay?
Then can you do this thing?
Now, hold on. Now, let's do this.
Yeah.
So, over here, on here, you have an equation that says UI, which is electrical potential energy, and you have 1 over 4 pi, let's just go right through the K, and you have K Q1 Q2 over R. Okay? Now, the force equation for charged particles is what?
The same thing with R squared.
Oh!
Joules.
Q2 over R squared.
Times the R.
So that gets you newtons. So it's the same idea. Okay? Same idea. Now, here's the problem. This is it. How do you calculate
MGH.
MGH? Right? Okay? This is the problem. And this is a huge problem. So if I lift this ball up, if I lift it up, what happens to the value of UG?
Increases.
UG increases.
The height increases, so it increases.
Okay.
Right? Bigger height, right?
Yeah.
I want to store more energy.
See, that's what I said, guys.
We heard, Gavin.
But here's the problem with this way of looking at gravitational potential energy. With this one, if I increase the distance, what happens to the value of?
Oh, it decreases.
Oh.
Why is that happening?
This is an inverse relationship. So UG MGH, if I lift it higher, that becomes a direct relationship. Olivia Pruitt, UG being G M1 M2 over D, if I lift it up, that makes it in what type of relationship?
Inverse.
Ah, that makes it an inverse relationship. Like, well, here's two conflicting ideas. In one situation, I lift it up, and UG increases. The other one, to look at it, I lift it up, and it decreases. Okay. Now, but here's how we reconcile this. Is that this UG here is measured from where? From the earth, right? Okay. The height above the earth, right? Okay. So now I want to jump ahead for just a second. So there's also, you can look at voltage, and when we get into the electrical side of this, is that if I take two positive charges, okay, so we're going to take a quick detour for a second. We're going to go into the electrical side of it.
Uh-oh.
I have two positive charges, okay? All right? They both have a positive charge. If I bring those two positive charges together, what am I going to be doing work?
Yes.
Yeah.
Yes. Why am I doing the work?
You have to apply a force over this.
Because do they want to get together?
No.
No. So if I bring two positive charges together or two negative charges together, okay, they don't want to be near each other. So the force that I have to exert is going in this direction. True?
Yeah.
Now, so if I push two positive charges together and I let go of them, what are they going to
They're
do?
going to shoot out like a spring.
It's like compressing a spring, and they're going to bounce back and they're going to go in the opposite direction. Would the same thing happen if I had Two negative charges.
Yes.
Same thing would happen, right? They don't want to be near each other. We saw this with the balloon. Okay, when I would charge the balloons and I would try and bring those together, they repel each other. And you don't have to worry about that with gravitational because the gravitational force is always attractive. But, so if I bring two positive charges together and push them together, let go, they're going to go flying apart, right? So the work that I do is in the opposite direction of, so I'm pushing them, right, in the same direction that they're going, but I'm storing energy. So let's look at this in terms of just a generic idea of energy, okay? Don't get wrapped up in the science for now. This is a generic idea of energy. So if I put distance here, how far apart they are, and the amount of energy that I store on the y-axis, what would that graph look like?
It's like this. Top left to bottom right.
Something like this?
Something like that.
Because as I decrease the distance, by pushing them closer and closer and closer together, OOI is going to get bigger, right? Okay? Now, would that graph be the same whether if it was two positive charges or two negative charges? Would that graph look the same way? Yes. Because of the fact that whether two negatives, two positive doesn't make any difference. Okay? Now, we're going to make somewhat of an analogy of a hill. Okay? So, here's this positive charge at the top of the hill. And I've got another positive charge that I want to push up the hill. Am I going to do work to push it up the hill? Okay, because it doesn't want to go near this. So me pushing that up the hill would be analogous to a normal idea of a mountain. So if I've got this boulder and I want to push it up the hill, I'm going to push it up the hill, but it's going to take work, right?
Indeed.
But as soon as I stop pushing it, what's the boulder going to do?
Crush you.
Let's just say I step out of the way and I let it roll down the hill. Would the same thing happen with two positive charges?
Yeah.
I've got to do work to push it up the hill, right? And if I stop pushing, what's it going to do?
Back down.
So two positive charges or two negative charges is analogous to pushing a boulder up the hill, right? True? Now, what would a kinetic energy versus distant graph look like?
It's like the opposite.
What?
Because think about it. Listen, at the very top, at the very top, right? Very top, you let it go. But it takes, when you push it up, it's slow.
Okay.
If you think about it.
So,
If you think about
if this is going to start up here, right? I've pushed the boulder up the mountain. So it's really, 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 really close. So as it rolls, what's going to happen to its velocity?
Increase. What
It's
happens?
going to increase. So that's going to go something like this. The farther away it goes, the faster it's going to go. Like me dropping this ball, right?
You mean like once you're done pushing?
Yeah, once you're done pushing.
Gotcha.
Once you're done pushing.
If you think about it, Shannon.
Okay? Now, and everybody's cool with this. This is not the problem. This is not the problem. Now, would you agree that for both of those, some amount of energy that you store plus some amount of kinetic energy is going to add up to a constant?
Yeah.
Like in the middle.
Always.
No.
Like your total amount of
Oh, okay.
Total amount of energy. Energy has to be conserved, right?
Oh, yeah.
Right? Now, if it's two positives or two negatives, if you look at how OOI is calculated, right? Okay? OOI is going to be a positive value. Okay? Whether it's two positives, two negatives, doesn't make any difference. So what that means is as one value goes up, the other one has to go down. So if I push the two positive charges together, I store more ooey, kinetic energy is going to go down. You can also view it as like throwing it. If I throw a positive charge toward another, okay, so imagine I have two positively charged baseballs, and I throw them together. As they approach each other, what's going to happen to the amount of kinetic energy? It's going to go down. But the ooey is going to go up. Cool. Nice. Now, again, this is not the problem. This is not the problem. Problem is when I have a positive charge and then I have a negative charge up on top of the mountain. Okay? Now, in this situation, why is this problematic? Because it wants to roll up the hill.
Oh,
right?
It's flipped because it's harder to go.
Oh.
It's like they're so attracted to each other.
Okay, so hold on to stop the bus. So, first off, start with this. This is going to be an attractive force, right? So if I don't do anything at all, and I just let go, imagine that I have a positive charge and I have a negative charge. The positive charge is going to feel an attractive force. But as it gets closer, what happens to the magnitude of that attractive force? It goes up. So as the attractive force gets bigger, what's the positive charge going to do as it approaches the negative charge? So going to accelerate. It's going to go faster and faster and faster. So if I want to keep that from happening, which direction do I have to push? So I've got to push, in effect, down the hill. Okay? Which seems weird. It's like, what do you mean I got to push down the hill? You've got to push down the hill. Because as soon as I stop pushing, what's it going to do?
Crush you.
It's going to go up the hill. Okay? So if you're talking just velocity and energy, and it's kinetic, right? You don't have to worry about gravitational. Everything's cool because everything's positive. But when you have positive and negative charges, that's where it gets a little bit weird. Now, let's go back to the big problem. The big problem is that ooey, you're dividing by r. Okay? Now, this is more of a theoretical construct and it has to do with the idea of something being infinitely far apart. So if you look at your equation sheet, okay? So you have this value of ooey, okay, which is kq1, q2 over r. So the way that equation plays out, number one, with ooey, which is electrical potential energy, because it's Q1, Q2 over R. Does ooey, in terms of electrical potential energy, could ooey be positive?
Yes.
Yes. In what situation could ooey be positive? If the charge is the same, either both positive or both negative. Okay? Okay? Now, could ooey be negative?
Yeah.
If they have opposite charges. Okay? So this is what's different from gravitational potential energy. Ooey can be positive or negative. You don't have to worry about that with gravitational potential energy. So that's one thing that you're going to have to think about. Now, the way this is defined mathematically, since you're dividing by r, if you look at how this ooey plays out, as the radius becomes smaller, what happens to ooey? It increases. Inverse. Right? Okay? But again, that's counterintuitive to what you all are used to thinking in terms of us. Okay? Now, here's where this gets more of a mathematical construct. Okay? So imagine that you have, and this is a huge imagination that you have to go with this, okay? But imagine that you have two positive charges that are infinitely far apart. Okay?
Oh, infinity stuff.
They're infinitely far apart.
Zero.
Okay? Infinitely far apart. Now, I'm slowly going to begin to push these things together. Okay?
So they're not.
So they're not infinitely far apart.
Finitely
They're
far apart.
infinite. Finitely but large. Far.
Yes. Why not leave it alone? Okay?
Okay.
Now,
It's not.
so here's the deal. So, to a certain extent, this boils down to from what position you measure R from. Okay? Right? So, in this situation, because of how you're going to measure R, you have to view it from being, hey, these points are infinitely far apart. So, the only way that this kind of makes sense, like I said, this is more of a mathematical construct than about anything else. So, if you look at measuring R, where would you have to measure R from so that as R becomes smaller, okay, or excuse me, as R becomes bigger, and we know this, R becomes bigger because you're dividing by R, then that becomes, if you're dividing by a bigger number, what's going to happen to it? Because you can't change what's on top.
There we go, small.
Okay, so as R gets bigger, UI gets smaller. So we need to find a way to measure R where if R becomes, but if you translate it and R becomes smaller, UI becomes bigger. So it boils down to the distance, it's where you measure that distance from. Okay? So what you're going to, and this is why I said it works well as a mathematical construct. You're measuring it from basically infinitely far apart. And you're pushing it from a distance infinitely far apart. And you're going to push that distance so that that distance, instead of being infinitely far apart, now becomes a non-infinite distance. Yeah.
Are we gonna have to do limits?
Do what?
Think calc, bro.
Okay, never mind.
No, you're not.
You're
You're not.
Just one.
Okay. Now, but the same thing happens if you look at UG being M1, M2 over D. So imagine that you have two masses that are infinitely far apart. Okay? They're infinitely far apart. And as you bring them closer, that attractive force is going to increase. So what you're talking about is that distance, instead of being infinitely far apart.
I'm testing it out.
Send him to the dungeon.
Okay. Oh, we would have named it Gavin if there was a dungeon.
Gavin.
So, the reason I point this out is so that when you see this on the equation sheet, and we'll spend more time talking about this on Monday, is that here's what I want, this is the big idea I want you to get out of this, is that there's two ways that you can look at UI in terms of the electrical value. One is, now imagine this, you have a positive and a negative infinitely far apart, versus two positively charges that are infinitely far apart. So if you have two positive charges that are infinitely far apart, you have to push them and you're going to store energy as they get closer. But if you have a positive and a negative and they're infinitely far apart, they want to come towards each other and you would have to push in the opposite direction from keeping them away. Living through.
Can you explain the parts of infinite distance, like what exactly?
Because how you view this, and like I said, this is you actually kind of have to do the calculus on this whole thing. But how you view it as being infinitely far apart. So in other words, you start not with them close together,